So now we're going to talk about differentiation of inverse trig functions. Hopefully you took the time to read through to kind of remind yourself of some things that we talked about previously about inverse functions. So talking about derivatives of inverse functions, here's your list. So when we take the derivative of arc sine, remember arc sine is the same thing as sine inverse. We get back this function u prime over 1 minus u squared. So notice that when we differentiate inverse trig functions, we're not getting a trig function back. We are getting some algebraic functions back. Same thing with arc cosine of u, negative u prime over square root of 1 minus u squared. Arctangent of u prime over 1 plus u squared. The derivative of arc cotangent, negative u prime over 1 plus u squared. Derivative of arc cosecant, negative u prime over the absolute value times the square root of u squared minus 1. And then the derivative of arc secant of u, negative u prime over the absolute value of u, all over this, the absolute value of u times the square root of u squared minus 1. This is in your textbook. It is on page 383 of your text if you don't want to copy this chart down. You did not print the notes out. Again, remember here just some things to remind you of. Arc sine is the same thing as sine inverse, and we're trying to figure out what angle gives us that sine value of x. These are all found from using implicit differentiation. I believe that your book goes through the finding of arc sine if you're interested in reading through that. And also just to know, like arc secant is the same thing as saying arc cosine of 1 over x, so using that reciprocal idea. So that's just kind of good for when you're using a calculator. So then differentiating each of these. So all I'm going to do is basically start plugging into formulas. If I want to find the derivative of arc sine of 4x, this equal sign does not need to be here. So if I'm trying to differentiate this function, the first thing I notice is that whenever I'm trying to differentiate arc sine, I'm going to get back u prime over the square root of 1 minus u squared. So for this function, it looks like my u is 4x, therefore my u prime will be 4, giving me the derivative of arc sine of 4x is 4 over the square root of 1 minus 4x squared. Don't forget to square both the 4 and the x, so 16x squared. Please remember that I cannot simplify this. All the time I see people want to say, well, the square root of 1 is just 1, and the square root of 16x squared is just 4x. I cannot break up and take the radical or take the square root of each piece unless it's multiplication in between. It does not work with adding or subtracting. So this would be my final answer. Looking at the next one, I have the arctangent of negative 3x squared. So same thing, I'm going to notice that arctangent is always going to differentiate to be u prime over 1 plus u squared. So in this particular case, my u is negative 3x squared. Therefore, my u prime will be negative 6x, giving me the derivative of arctan of negative 3x squared is negative 6x over 1 plus, if I square my u, squaring a negative 3 gives me 9, squaring an x squared gives me x to the 4th. And remember, again, I cannot simplify, I cannot reduce these. I can only reduce with multiplication. I cannot reduce with adding and subtracting unless I can factor something out and then reduce, which I can't factor anything out of this. So again, this would be my final answer. Moving on to look at 2 additional examples. If I'm taking the derivative of arc sine of square root of x, again, I know that whenever I have arc sine, it will differentiate to be u prime over the square root of 1 minus u squared. So with this particular function, I see that my u is the square root of x, or x to the 1/2. Therefore, u prime will be 1/2 x to the negative 1/2. So I'm going to go ahead and plug that into my formula, and I get 1/2 x to the negative 1/2 all over the square root of 1 minus, I'm going to go ahead and square my u. Notice that when I square something with a 1/2 or something under a radical, they cancel, so giving me 1 minus x. So now from here, it's kind of funky to have this fraction on top, and it's also kind of funky to have this negative. So what I can do is I can say that, isn't this the same thing as multiplying by 1/2? So can't I put the 1 on top and 2 on the bottom? And then can't I move this to the bottom to make it positive? If I do that, I get a final answer of 1 over 2 times the square root of x times the square root of 1 minus x. I can leave it like this, or I can distribute this into my radical, giving me a final answer of 1 over 2 square root of x minus x squared when that x gets distributed in. This is probably the best final answer. It looks the nicest. It's simplified the most. And then looking at another example with this, I see that I want to differentiate arcsecant e to the 2x. So again, first thing I'm going to notice is that whenever I differentiate arcsecant, I get u prime over absolute value of u square root of u squared minus 1. I find that if I write my formulas out, they help stick in my mind better. So from here, then I see that my u is e to the 2x. So my u prime is going to be 2 e to the 2x. I got that from using the chain rule, so I would have to then say that u is 2x, v is e to the u, the derivative of 2x is 2, the derivative of e to the u is e to the u, so taking u prime times v prime does give me 2 e to the u. Filling 2x back in for u gives me 2 e to the 2x. And I can show you that further in class if that didn't make sense, my verbal explanation. But now that I know that, I'm going to go ahead and plug in, and I have u prime over the absolute value of u. Well, I know e to the 2x is going to be positive because it is that exponential function. So my 2 looks kind of messy, so does my e, sorry about that, times the square root of u squared, so e to the 2x squared, minus 1. So from here, I see I can cancel out an e to the 2x. I also see that power to a power, they just multiply, so that'll give me e to the 4x. So doing that, I will have a 2 on top, the square root of e to the 4x minus 1 on the bottom. And I don't see anything else I can do with this, so I will stop here with my final answer. Looking at 2 more examples, if I'm asked to differentiate arc sine of x plus x square root of 1 minus x squared and simplify as much as possible. So looking at this, so this is going to be an example of one that we can do quite a bit of algebra with to keep continuing to simplify down. So I'm going to go ahead and first say, all right, if I'm differentiating arc sine, I know that arc sine is always going to be u prime over the square root of 1 minus u squared. So I notice that I have a big old crazy u on this one. So my u, actually, because I don't have parentheses around this, I don't have a crazy u. My u is just my x. So that actually works out nice. And my u prime would be 1. So this is going to be fairly basic to differentiate. However, I am going to have to use the product rule to differentiate this piece here. So I'm going to go ahead and work through that too before I start my differentiating. So with the product rule, f of x will be x. G of x will be 1 minus x squared to the 1/2, which means in order to find g prime, f prime's easy, I'm going to have to use my chain rule also. So u equals 1 minus x squared, v equals u to the 1/2, u prime equals negative 2x, v prime equals 1/2 u to the negative 1/2. Therefore, g prime of x is, when I multiply u prime times v prime, my 2's will cancel. So I'm just going to go ahead and say negative x times u which was 1 minus x squared to the negative 1/2. So now I'm going to go ahead, now that I have all that information, now I'm actually going to differentiate. And I'm going to say y prime equals, so differentiating first the arc sine of x, 1 over the square root of 1 minus x squared, plus, using my product rule, derivative of the first times the second, so 1 times 1 minus x squared to the 1/2, plus derivative of the second times the first, so negative x squared, so I wonder if I can, yeah, it won't let me erase that. So negative x squared times 1 minus x squared to the negative 1/2. Continuing from here, I am going to go ahead and move this to the bottom and make that positive, and also turn it into kind of a square root. So then I will have 1 over the square root of 1 minus x squared plus the square root of 1 minus x squared, changing that 1/2 to a radical, plus a negative is minus x squared over, again moving this to the bottom, the square root of 1 minus x squared. From here, I notice that these have a common denominator, so I can put these two together and share that common denominator. So 1 minus x squared over the square root of 1 minus x squared plus the square root of 1 minus x squared. From here, I see that these have a like term. So this is essentially on top, excuse me, 1 minus x squared to the 1. So if I have on top 1 minus x squared to the 1 and essentially 1 minus x squared to the 1/2 on the bottom, I can subtract, giving me 1 minus x squared to the 1/2, which is just 1 minus x squared under a radical, plus another 1 minus x squared. These are like terms, so I can combine them, giving me a final answer of 2 square root of 1 minus x squared. And that looks as simplified as I can get. So like I said, a lot of algebra on that one. Many of our rules coming into play. Do you know how to differentiate a trig, inverse trig? Do you know how to use the chain rule? Do you know how to use the product rule? So all kinds of things going on up here. So this is kind of a great example in regard that it pulls kind of everything together. So then looking at one application problems with inverse trig functions, what about if I'm asked to find the function's relative extrema? Do you remember how to find relative extrema? So that's when we're talking about where is it changing from increasing to decreasing. So very first thing I'm going to do is I'm going to find the first derivative. So I'm going to acknowledge that arctangent of x always differentiates to be u prime over 1 plus u squared. Okay. My 1 looks like an 11, sorry. From there, I'm going to have to use my chain rule. So my inside function is going to be arctangent of x. My outside function is going to be u squared. My u prime is going to be the derivative of x, which is 1, over 1 plus x squared. My v prime is going to be 2u. If it is confusing to you to have a bunch of u's and u primes, change a letter. We can use whatever letter we want for a variable. I do not have to use u and v for my chain rule. Okay, I could say t and v. Doesn't matter. So then from here, completing my chain rule, I get y prime equals derivative, u prime times v prime. So that gives me 2 arctangent of x for my v prime times 1 over 1 plus x squared. So 1 plus x squared. So if you remember from here, when we're going to try to figure out where we could possibly have inflection points, we have to find our critical numbers. So I have to set y prime equal to 0. So doing that, I get 2 arctangent of x over 1 plus x squared equals 0. So critical numbers, remember, they're going to exist either where my function equals 0 or my function is undefined. My function's never going to be undefined. That's never going to be 0. So I'm really trying to ask myself, when does, because I can divide by 2, and say, when does arctangent of x equal 0? Well, if I remember, may I look up or find a graph of arctangent of x, which again, hopefully you read those first couple introduction pages to the section, you'll see that arctangent of x is 0 when x equals 0. There is a page, it's I believe page right around somewhere between 380 and 382 in your book where you can look at that graph. So x equals 0. So now that I know where my critical numbers are, I'm going to change colors. I'm going to go ahead and set up my intervals. And I'm going to go from negative infinity up to 0. And from 0 up to positive infinity. I'm going to pick my test point. Let's say I pick negative 1 and 1. I'm going to plug my test point into my derivative. So I'll do f prime of my test point, TP. So plugging negative 1 into my derivative, so my derivative's up here. I know that I'm going to have a positive on the bottom. Arctangent of negative 1. Arctangent of negative 1 is going to be a negative. So I will end up with a negative times, a negative divided by a positive. And that will give me a negative here. If I plug a 1 in, arctangent of 1 is positive. Of course, I know my bottom will always be positive. Positive divided by positive gives me positive. Again, there is that picture of the arctangent graph on page, I believe, 381. I could also, in terms of how do I determine what arctangent is, what is my sign at negative 1, the way you can think of it is arctangent is asking me what rotation gives me a tangent value of negative 1. Well, I know that I have to rotate down to negative pi over 4 to get a tangent value of negative 1, so that's where that negative is coming from. How do I know it's positive? What tangent value gives me 1? Well, if I think about my unit circle, where is tangent 1 at? At pi over 4. So that's positive. That's where else another way I can think of that. So either looking at a graph or thinking about it in terms of what does arctangent mean, what would the value be on my unit circle. So then from here, now that I know this is negative, I know it's decreasing. If it's positive, I know it's increasing. So if it changes from increasing to decreasing, I know I have a relative minimum at the point 0, comma. In order to figure out what other point, I have to plug 0 back into my original function. So arctangent of 0. Well, I know what rotation gives me a tangent value of 0. I know it's 0. 0 squared is 0, so I do end up with a relative minimum at 0, 0. And that is it for your notes on inverse trig functions, differentiating them. We will look at doing some problems and some examples in class the following day.